The 22-minute cycle of GPM J1839-10 presents significant technical challenges, requiring telescopes to track celestial coordinates with extreme precision for multiple hours. Radio interference from human activities, satellites, cell phones, and other technologies can mask the subtle signals, necessitating sophisticated filtering algorithms at each observatory. Coordinating timing between facilities adds another layer of complexity. Dr. Alexandra Rodriguez, coordinator of the National Radio Astronomy Observatory, notes, securing time on major facilities requires demonstrating exceptional scientific merit. For this object, we've received priority access across facilities that normally have months-long waiting periods. These synchronized observations across wavelengths provide insights impossible to gather from a single facility. While radio telescopes track the primary signal, X-ray observatories like NASA's Chandra and ESA's XM search for high-energy emissions that might accompany the radio bursts. The strength or absence of X-ray counterparts significantly constrains theoretical models, as magnetars typically produce powerful X-ray emissions. Optical telescopes contribute by searching for visible counterparts. The European Southern Observatory's Very Large Telescope in Chile has conducted deep imaging of the region, helping determine whether the radio emissions originate from an isolated neutron star or one with a companion, like determining whether a mysterious sound comes from a solo instrument or an ensemble. The analysis extends beyond simple detection to sophisticated techniques that extract maximum information. Polarization measurements reveal the orientation of radio waves, providing critical information about magnetic field geometry. Dr. Miguel Sanchez of the Max Planck Institute explains, we're seeing indications of extraordinarily complex field structures that don't match conventional models. Spectral analysis examines how signal strength varies across frequencies, creating a fingerprint that helps astronomers understand the emission mechanism. GPM J1839-10 shows unusual spectral behavior with dramatic variations across the radio spectrum, narrowing the field of potential explanations. High-precision timing analysis measures exactly when each burst begins and ends across multiple telescopes. Dr. Hiroshi Tanaka of Japan's National Astronomical Observatory points out, we're measuring arrival times with microsecond precision, allowing us to detect subtle timing variations that could indicate precession or other complex rotational behavior. The Green Bank Telescope in West Virginia contributes vital observations with its 100-meter dish. Its exceptional sensitivity detects subtle features within each 5-minute burst that smaller instruments might miss, revealing complex substructures, momentary brightening, and dimming patterns that may correspond to physical processes on or around the object. South Africa's MeerKAT array brings valuable imaging capabilities with its 64 interconnected dishes, creating detailed radio maps of the surrounding sky to determine whether nearby objects interact with GPM J1839-10 or affect its emissions. This global collaboration extends to data analysis, with specialized computing clusters processing massive datasets. Dr. Rafael Moreno of the Barcelona Supercomputing Center describes the challenge. We're developing new machine learning algorithms specifically for this data, as traditional methods weren't designed for objects with such long periodicity. One valuable insight has been confirming the object's radio spectrum across an unprecedented frequency range. Dr. Elisa Chun, who led observations with China's 500-meter aperture spherical telescope, FAST, explains, we've characterized the emission from 50 megahertz to 1.5 gigahertz, ruling out several theoretical models and constraining the emission mechanism. By pooling data, astronomers detected microsecond level variations in burst arrival times, suggesting the object may be precessing, wobbling slightly as it rotates, potentially explaining some unusual emission properties and revealing details about its internal structure. The Westerbork Synthesis Radio Telescope in the Netherlands contributed critical polarization measurements showing nearly 100% linear polarization, strongly supporting the magnetar hypothesis. Dr. Willem van der Merwe notes, This polarization signature is exactly what we'd expect from radiation produced in a magnetar's extremely strong magnetic field. Surprisingly, NASA's Fermi Gamma Ray Space Telescope found no gamma ray counterpart to the radio bursts. Significant because typical magnetars produce powerful gamma ray flares during active periods. This absence suggests GPM J1839-10 may represent a previously unknown magnetar subclass with fundamentally different emission properties. Ultimately,